now we're going to dig deeper in how to actually apply Kirchhoff's rules in a broader range of situations. Situations where we don't necessarily have a pure series or a pure parallel circuit, or it's not just resistors. Maybe there's more than one power supply, kind of going through these. We're still only going to work situations that have just resistors and power supplies for right now. So anytime we apply Kirchhoff's rules, the first thing we have to do is draw a circuit diagram. Or there's probably going to be a circuit diagram already provided for you. The second thing you have to do is to choose an appropriate direction of current through each branch of the circuit. So this one's going to be kind of the weird one. So let's say that I have some sort of weird and funky circuit. I'm going to do something kind of crazy. We're going to have a couple different power supplies going through. Maybe some branches. All right, so a bunch of kind of funky things going on. So what I mean by this is I'm going to choose where I think the current is going. So I'm going to choose, okay, like say for each one of these resistors, I'm going to assume that the current for this one is going that way. And since that's the positive side, I'm going to assume that the current goes this way out of that battery. So they're going to meet up and go this way through that branch. And then it's going to split. Let's go that way, come back this way, come back that way, come back that way. So I'm going to assume that I know where the current is going through. Now, if one of these was wrong, then what would happen is when I go through and do my calculation, if I've done everything else right, I'm going to get a negative current. So for example, if I assume that this one is that way, but the current's actually flowing the opposite direction, which actually I don't see there's any way that could. But if it was actually going the opposite direction, I assumed it was going this way, this one would calculate out as negative, assuming I did everything else right. So this is not the most critical part, but it is something that you are going to have to do in order to apply the rules. Then what you're going to do is you're going to apply Kirchhoff's junction rule. And so you need to choose at least one junction. And depending on how complicated the circuit is, you may have to use more junctions. Usually don't need to do every single junction because some of these junctions are going to be the same. So for example, if I was solving this crazy one that I drew right here, I would definitely choose like this junction, that junction, because those are junctions. But like this junction right here is going to be the same as this junction. And this junction's the same as that one. So really, I only need to do those two junctions. Those are only really two unique junctions that I have. So I don't have to necessarily write one for all of them, but if I only do one, and there's several more out there and I find I'm missing information, I might need to write another one. The next thing I need to do is I'll need to apply Kirchhoff's loop rule. So the loop rules are going to be needed at least one. But more likely, you're going to need one loop rule for each major branch that contains the power supply. So for this crazy one I drew, I'm probably going to need one here. And this one has two power supplies, so I definitely have to include that one. So that's going to be a useful one. I might also do this one, and I might do that one. But because I have a second power supply, it might be handy to do this one as well, or maybe that one. So this one actually has a bunch of different loops that I could do. The point of this is with these equations that you end up writing, you're going to create a system of equations, and you're going to need enough equations to figure out all of your unknowns. So you may need some, you may need all. It just depends on how much information the question gives you and what it's asking for. So then you solve the system of equations. So how do we apply the loop rules? So like I said, you have to choose an appropriate direction of the current through each branch, and then you're going to need to write a loop. So this table right here gives you kind of a little cheat sheet for how to use the rules. And this is something that you are going to need to memorize. So some of this you'll memorize just by practice. And I don't necessarily remember all of this. I remember one of these pairs. for each of these lines, and then I remember, oh, if it's the other way, it's opposite. So how do I read this table? So the first thing I do to read this table is I first have a resistor. So this is, once again, for the loop rule. So I have a component in my circuit. Let's just say it's something really simple right here. And I have chosen already a direction of current. So I'm going to draw that right here as kind of this purple to kind of match the purple right here. So this is the current through my resistor. So I'm going to call that one I1. So there's also going to be a travel direction for my loop. So I'm going to use this right here for my travel direction. So I'm going to choose a loop that is in the same direction as the current, if I can. So I'm going to make a loop that looks like that. So if I get to a component and the current that I have drawn is in the same direction as the travel direction, that is a voltage drop. This is a voltage drop. So I have delta VR would be minus IR when I write that in the equation. So here, the way I have this drawn in this example, my travel direction would be from top to bottom as I pass through that resistor. So when I write a loop rule for this loop, that is going to be a minus I1 R1 through that component. Now, if I look at an EMF source, now I'm going to skip the right side here for a sec because the left side is kind of how things usually are. If we've done everything right, and there's nothing funky going on, this is how it'll work. So with a power supply, remember the short line is the negative and the long line is the positive. If I look at my travel direction, if my travel direction goes from negative to positive, then my power supply is a voltage rise. And I would write positive E. Remember that E is for EMF. Okay, and we'll talk a little bit more about that EMF here in a little bit when we talk about internal resistance. So I'm going to get that E for EMF, but it is really a voltage, okay? But it's the voltage of the power supply, EMF. So when I look at this, the travel direction for the circuit up here that I drew, when you look at that power supply, is going from negative to positive. So that is a voltage rise. So that would be plus E. There are no other components in my loop, so then that has to add up to 0. And I have now written a loop rule. So let's look at the other side. That's normally what happens. Now when you get really complicated circuits like this guy up here, you start running into funky situations, especially if you have multiple power supplies and lots of different branches. So this right here is basically what happens if the normal doesn't work. So let's take my circuit again, this little just simple one that I did. And let's erase my travel direction. And choose a different loop. I'm now going to choose the loop that goes the opposite direction of my current. Now, that's not something I would normally do, but it may end up that way if I have a complicated circuit and I don't remember, or I can't tell which way the currents go because maybe there's multiple power supplies. So if I do that, I'm still going to go through and apply the rules. So I'm going to pick my travel direction. This time I'm going to use yellow for my travel direction. When I look at that resistor, no, sorry, my travel direction is the opposite way because I did it the other way. Okay, if I look, my travel direction is from bottom to top. So that's my direction of travel. Notice that my travel direction and my current are in opposite directions. When my travel direction and my current are in opposite directions, I write this with a positive IR because it's acting like a voltage rise. It's really not a voltage rise, but based on the way you do that, it's acting like a voltage rise for that direction. So for that case, I would write positive I1 times R. Okay, whatever that resistance is. Now, for my voltage source, I notice that my travel direction is going from top to bottom. So that's my direction of travel. And I'm going from positive to negative. So when I look at this, when my travel direction goes from positive to negative, my voltage source is acting like a voltage drop because it's going from higher voltage to lower voltage. So my change in voltage is actually negative. So I would have to write that as a negative E. And then those are the only two components in my loop, so that's going to have to add up to 0. Now notice that because I changed the direction, my signs are both exactly opposite. So if I was to rearrange these equations, both of these equations tell me that E is equal to I1 times R. So nothing changes in my calculations for my circuit because I picked a loop direction to the opposite way. But if you have a lot of components and a lot of loops and things, incorrectly applying your rules are going to end up with sign errors. And some of those sign errors could end up causing your values to come out wrong in the end. So this is the way it is most of the time. So if you remember those and realize, oh, if it's the opposite, I flip the sign, you'll be fine. It minimizes the amount of stuff that you have to memorize. So what we're going to do is we're going to apply Kirchhoff's rules to this 2-resistor series circuit. Now, if you have learned circuits before, you probably learned there are easier ways than what I'm about to show you to solve this problem. For example, if this was all I needed to do, I could easily solve for the current leaving the battery by finding my equivalent resistance, which is just R1 plus R2. And then I would say, oh, well, my current coming out of the battery is just my voltage of my power supply over my equivalent resistance. And then I would know that my equivalent resistance is R1 plus R2. I have the voltage of my battery, and I could do that. That's wonderful. But what I'm telling you right now is the problems that you're expected to be able to solve cannot always be solved using just the rules for series and parallel, even the series and parallel applied to complex circuits. Once you start adding in more extra power supplies, once you start adding in capacitors and inductors, these simple things that you might have seen in high school or in like even AP physics will not always work. So please bear with me, and you need to be able to solve all problems with this method so that we are able to build up to the harder problems. Okay, so please don't skip this just because, oh, I was able to solve that problem 3 years ago. Okay, please don't do that. We're going to practice with easier circuits and build up to the more difficult circuits that are in the derivation packet. So please, that's my caution for you. All right, so if I was to solve this problem using the procedures on the previous slide, what we're going to do is we are going to assign the direction of current I. Okay, and that current I is going to then be through each of these same components. Now, it's generally going to flow in the direction of conventional current from positive to negative. If you don't know, guess. Okay. If they give you a current that's negative, negative current just means it's flowing in the opposite direction. Then the next thing we do is we pick a travel direction for our loop. It can go either clockwise or counterclockwise along this loop, but remember, best rule, I guess you could say, is that you want your travel direction to be in the direction of current in as many loops as you can. So in this case, we have only one loop, so we're going to go clockwise around this loop because that's the direction that we're assuming current is flowing. So then we want to apply the voltage rule. So when we apply our voltage rule, the battery voltage is going to be positive if you travel from the negative side to the positive side. Negative side to positive side. And then our resistor voltage is negative if you travel with the current. So when we go across the current right here, the current and the loop direction are in the same direction, so that is going to be a negative voltage for that. So if we apply that rule, then we're going to get E minus V1 minus V2 is going to be 0 because you just keep on going around that loop. Now, one thing when you're doing this, please, please, please do not include any numbers. Do everything with symbols because that is one of the requirements for problem solving in this class. You must do everything non-numerically in order that you are not skipping through steps that could earn you points. Okay, so please write these equations out non-numerically if at all possible. If they don't give you symbols, create your own. Call this one resistor 1, this one resistor 2, and go through it. All right, so here we're going to continue on. So we have our current and we have our loop direction, and now we need to apply our junction rule. So with our junction rule, there are no splits in our current, so the current is the same everywhere. So that basically just tells us that I1 and I2 are going to be equal to our original current I. We can then apply Ohm's law to every component in the circuit. So we can define that V1 is going to be I1R1 and V2 is going to be I2R2, but because the currents are the same, we can just call them I. Now, you could have applied this in the previous step. So if I was working through and I'd gotten really good at this, I could have started my equation with E minus I1R1 minus I2R2 is equal to 0, but I still would show that I am using the same I for that. Okay, so I would make some sort of statement that says I'm going to assume that I is equal to I1, which is equal to I2, because that is an application of the junction rule. So I would write that somewhere. Okay. So you could start with lots of different versions of the loop rule. Just make sure that it's clear what those assumptions are. So then you can substitute into the loop rule equation, which is what I've done here again for you. And then this equation has only one unknown, which is I. So we can then rearrange that equation to solve for I. So you can factor the I out of each term here. And then you can add that term to the other side. And then divide by R1 and R2. And you get I is equal to E over R1, R2. Which is the same thing as E over REQ for this series circuit. You get the same result. This is a little more lengthy of a process at the beginning when you are still figuring things out. But once again, this is the process that you have to use when working with more complicated circuits. You won't be able to use the simplified version that you might have done previously, or you might see on other videos like Khan Academy and things like that, for every circuit in this class. Then we can just plug in. Remember, you must always show your substitution of values. So E is 12 volts, and you have 2 ohms and 4 ohms on the bottom, so we end up with a current of 2 amps. You could then also go through and find different things. You could find the voltage drop across R1. You could find the voltage drop across R2. So there's more that you can find. You could find the power dissipated by each resistor. So if I wanted to find delta V1, I could just use Ohm's law, because that's I times R1. Once I know I can find delta V1. I could use power is current times voltage. So I could do I1 delta V1 to find the power dissipated through that resistor. So there's a lot more things you can do with this circuit than just find current. But in that case, what this one was looking for. So let's look at another one. This one actually has two different voltage sources. So you can do this with series circuits. You can do this with parallel circuits. In this case, this is a series circuit. So each of these power supplies is facing the opposite direction. So these two voltage sources are actually working against each other. So I don't actually know which direction the current is going to flow in the circuit. If I had numbers, the current would flow in the direction that the current would flow from the larger voltage source. So if this was like a 6-volt power supply and this one was a 12-volt power supply, the 12 volts would basically win out, and so my current would flow in that direction. But if I switch those around and this one was 12 volts and this one was 6 volts, then my current would flow in the other direction. When you have more complicated circuits, where maybe I have some other components in some of these branches, let's put something there. You really don't know if you have a lot of unknowns which of those power supplies is going to win out. If I was to guess, it's got to come from positive to negative for this part here. I would assume it's going from positive to negative for that part there. So I'm going to assume that because both of those would be going from positive to negative, that it would have to come through this way to get through here. But if this was a really, really large voltage source and this one was a really large voltage source, it's actually possible that this one could come out here and that could actually force the current to flow through that one. So I really don't always know for sure unless I'm given values. And sometimes they'll give you the value of each voltage source, or sometimes that's what you're looking for, is what's the missing value. So it doesn't matter which way you pick. Remember, the current direction will sort itself out and you might get a negative value for current. That just means, oh, my current was going the opposite direction than I thought through that circuit. So just kind of practicing, let's assume that our current is going this way. Just because. So if I'm assuming that my current is going that way, and I wanted to write a loop rule for this, I do know that there are no junctions, so the current is going to be the same. So I'm going to assume that I have that same current I going through all parts of this circuit. So what I would do is I would say, okay, I'm going to have whatever this VB is, that one, if I look at my loop, I'm going from negative to positive. That one's acting like a rise. This one here is going from positive to negative. That one's going to act like a drop. And I'm going to assume that because my travel direction is going in the same direction as my current for all of my resistors, I could write this equation is going to be a positive VB minus VA, because that one's going the opposite direction for my loop, minus IR3 minus IR2 minus IR1 is equal to 0. And then if I wanted to, I could then factor out I. If I wanted to find that current I could do that. If I was looking for a missing voltage, I'd have to know a current. It really just depends at that point what I know and what I don't know. But that's an example of how you might have to make a choice based on an unknown in a situation. So here's another example of a series, but a more complicated series with those two batteries. I want to, in this case, find my voltage from A to B. If I was to start this problem going through our problem solving procedures, I'm going to set this up non-numerically. In that case, I'm going to call this one V1, V2. Actually, I'm not going to even use E's. I'm going to use E's instead of V's because these are voltage sources, so they're EMFs. I'm going to call this one E1 and this one E2. I'm going to call this guy R5 because it's 5 ohms. I'm going to call this one R10 because it's 10 ohms. For me, that's easier. If I wanted to go through and write that rule, then I'm going to get a positive E2, a minus E1, and then I'm going to get minus I times R5 and minus I times R10. And that has to add up to 0. So starting here at that, going through that one backwards and going the correct direction through both of those. Okay, so then I made it back to my power supply. So I'm looking for VAB, which is actually this component right here. That's VAB. I could have just left it VAB in that equation, but the problem is that would give me 2 unknowns in my equation. I wouldn't know I and I wouldn't know VAB. So by substituting in IR10 using Ohm's law, I only have 1 unknown, and that is just I. So I'm actually going to solve for that first. So I can say that E2 minus E1 is equal to IR5 plus IR10. Adding those to the other side, I can then factor out the I. So I get E2 minus E1 is equal to I times R5 plus R10. Then solving for I is going to be E2 minus E1 over R5 plus R10. Now I can plug in 9 volts minus 6 volts over 5 ohms plus 10 ohms gives me 3 volts over 15 ohms, which is 0.2 amps. So I found the current in the circuit. It's 0.2 amps. Notice that even though I had numbers for most of this, I did not sub in numbers at the start, because you want to make sure you're showing all of your steps algebraically, plugging numbers in only at the end. So then my VAB, using Ohm's law, is just going to be I times R10. So plugging in I is 0.2 amps times my 10 ohm resistance. VAB is just going to be 2 volts. If I was to check, since I know that my voltages all have to add up around this circuit, I can check to make sure I did this right, because the voltage drop across my 5 ohm resistor, I times R5, is going to be 0.2 amps times 5 ohms, and that just adds up to 1 volt. So my voltage rise is 9 volts. I have a voltage drop of 6 volts here, 1 volt here, and 2 volts there. So my voltage rises equal my voltage drops, because this guy acts like a voltage drop because it's going in the opposite direction. So we're going to take a moment here to discuss our ideal versus real voltage sources. And this came up a little bit in current voltage and resistance in that first lesson on kind of basic circuits. And we're going to go a little bit more in depth, because now that we know Kirchhoff's rules, we can understand a little bit more why these behave the way they do. So in an ideal voltage source, the voltage does not depend on the current flowing. So most real voltage sources will kind of suffer when you start adding more components in, but we assume that with our ideal batteries that this doesn't happen, okay? That no matter how much you plug into it, how much current you're drawing from it, you're going to have the exact same voltage no matter what. In a real battery, the voltage is going to depend on current, and in most cases, the voltage is going to decrease with increasing current when the load on that voltage source is higher. So how do we model a real battery? Well, what we assume is that that voltage drop from the ideal is caused by internal resistance. That inside of your battery there is some resistance that is not being accounted for in our kind of printed voltage. So like if I tell you that you have a 9-volt battery and you're actually getting 8.9 volts out, that small difference in voltage for a brand new fresh battery is going to be due to the internal resistance within the material of the battery itself. So we model a battery with this dashed green line. So if you were to model a battery, you would have an internal resistance, which is always represented with a lowercase r, and you would have the EMF E of the power supply. So the EMF is that ideal battery voltage, and then that internal resistance is going to essentially steal voltage from the source based on how much current is flowing through that battery. So based on that current draw. That voltage of that ideal battery is the electromotive force. That is the EMF that we have been using. And that lowercase r is our internal resistance. So you can see that if I was to take a multimeter and measure the voltage from one terminal of the battery to the other, my measured voltage is not going to equal the EMF. That measured voltage is going to be smaller because of that internal resistance. So we assume that the electromotive force of a voltage source, so the EMF, is the potential difference, the voltage it produces when there's absolutely no current flowing. But remember that EMF is not actually a force. They just, like a lot of things in physics, have been using it for so long that they just can't get rid of it. So we call it EMF, not electromotive force, if at all possible. And we use that curly E for that. Can you measure EMF? Yes, so you can hook up that voltmeter. So what happens is, as soon as you connect the voltmeter itself is going to experience a current through it because you have a complete circuit. You can measure the voltage, terminal voltage VAB. You cannot measure the EMF directly. If you had an ideal voltmeter, you could theoretically measure E because there would be no current flowing through that part of the circuit. So if we're doing an ideal power supply, we assume that the internal resistance is negligible, and so then we would just have E. But if we were asked to find the terminal voltage or use the terminal voltage to determine the internal resistance, we can use Kirchhoff's rules for that. So here's an example. We have a battery is known to have an EMF of 9 volts. It says 9 volts on it. We put a 1 ohm resistor to make a circuit with that battery in there. And we want to figure out the internal resistance of the battery. So I'm going to hook up a multimeter to either side from A to B of that battery. So this could be your, positive side of your battery, and that's the negative side of your battery, right? So you're connecting to the terminals of your battery. There's a little dot there for the tip of your battery. And we are getting a reading, VAB, as 3 volts. So what you're going to do is you're going to write a loop rule for that loop. Now, I'm going to assume that this is the positive side of my battery right there, even though there's that little internal resistance. So I'm going to choose my current to be going clockwise, and therefore my loop direction is also going to be going clockwise. So what happens is my current across that internal resistance is in the same direction as my loop direction. So I'm going to do minus IR, and then I'm going to do the current through resistor R1 with this 1 ohm resistor, capital R, on the outside. That's not inside the battery, that's an external resistor. is also going to be in the same direction as that loop direction, so I get minus IR. And then our terminal voltage, VAB, is going to be the difference in potential from A to B. And it is just going to equal I times R, because if I measure the terminal voltage here, whatever potential is at A is the same as the potential here, assuming that our wire has no resistance. And everywhere that is connected to point B must have potential VB. So therefore, VAB is going to be the same thing as delta V across that resistor. So we can define VAB to be just IR for this resistor right here. So then if you just kind of go through and sub in, you have E minus IR is 0. We know that IR is going to be E minus IR. Okay, so just kind of solving, we're adding this guy to the other side. So little r is going to be E minus IR over I. And then what you can do is you can just kind of split those up. So you get your R is E over I minus R. And we know that capital I is going to be VAB over R, okay, using our previous relationship. So then we can take this and we can sub in here for I. The order doesn't really matter, but it's just nice to have that I in only one location. So then we get that R is going to be E times big R, because you're going to have to flip this expression and get the VAB on the bottom minus R. So you get that little r is big R times E over VAB minus 1. You can plug in, and then you would get that R is 2 ohms. However you go about this algebra can be different. You don't have to do it like this. This is just the way that it was laid out in this PowerPoint. It's probably not the way my brain would have worked, so if it wasn't the way your brain worked, don't worry about it. But this is the big assumption right here. This is the part of this derivation that most people would struggle with, is recognizing that the voltage across here is VAB and the voltage across here is VAB, so that your VAB is just I times R. For I is the current in the circuit, and R is that 1 ohm resistance out there. So that's information that we would have to know. Now, 2 ohms would be a huge internal resistance, because depending on whatever current that you end up with, that is going to give you a big drop in voltage. So that's probably unlikely. So what I'm going to do is I'm going to show you now kind of the alternate method to solving resistor-only circuits where you have a single power supply and an array of resistors. So this method is still based on Kirchhoff's loop and junction rules, but we're going to start primarily with the assumption of equivalent resistance, and we're going to find the equivalent resistance of the array and then use Ohm's law to find anything else that we need. So with this, this method will not work at all if you have multiple power supplies, especially if they're in funky orientations. It will not work if you have capacitors. It will not work if you have inductors, which are electromagnets. You are allowed to use this method anytime you want, unless I specifically tell you in a problem that you must set up the junction and the loop rules. Now, let me give a caveat for that. If I ask you for the loop and junction rules, you have to write them. But if then I say, okay, solve for this unknown, and you know you can use this method, and you don't have to use the rules that you wrote, you can do other methods, that's fine. Because as long as you're applying proper physics, the actual method used to solve the problem works, unless it specifically says, use this method, which I've done. Like I've said, using Gauss's law, solve this. So just be aware of that. And beware that this doesn't work in every situation, that you still have to be able to write loop and junction rules, which is what the derivation packet will help you practice. So with this problem, I can see that there's one power supply and there's a whole bunch of resistors. There's a lot going on here. Our goal is to calculate the current drawn from the battery and the current in the 6 ohm resistor. This problem, with what I know here, I could find the current through every single component. I could find the voltage drop across every single component. There are so many different things I can do with a circuit like this. So when I'm working problems, there are two main things I can work with. I can work with equivalent resistance. So I know that in series, my resistances add up. So my equivalent resistance is the sum of all of my individual resistances. I also know that in parallel, the reciprocal of my resistances sums. I also know that I have Ohm's law, and Ohm's law tells me that the voltage of any one individual component is the current of that component times the resistance of that component. And then I also know, if I'm working with equivalent resistance, if I have a whole circuit, that the voltage of my power supply is the current draw from the power supply times my equivalent resistance. Okay, those provide kind of the nitty-gritty of everything that I can do. Now, because I have both series and parallel components in here, I'm going to have to kind of break this into pieces to analyze it. So the first thing we're going to do is assign a variable to each of these components, because although you can work these numerically, it communicates at the start what it is that you're doing and what you're looking for a lot better, especially because there are some cases where I could have like an 8 ohm resistor here, and then I've got these 8 ohm resistors. Like which 8 ohm resistor are you talking about? I don't know. So what I'm going to do is I'm going to just kind of number these off. So I'm going to call my power supply just E. There's only one of them in this case, so I don't need E1 or E2. And then I'm going to go R1, R2, R3, R4, R5, and R6. So when I'm trying to find equivalent resistance with a complex circuit with a lot going on, I need to picture about kind of this nested idea. There's circuits inside of circuits inside of circuits. So when I first look at this, I see the most kind of nested part of this is this parallel part right here. Those two 8 ohm resistors are in parallel with each other. If I could find a single resistor to replace those, I would call that equivalent resistance R45. I'm not just going to call it REQ because I'm going to find a bunch of different REQs here. And then if I ignore R4 and R5 and I just look here, what I've done here, because I've replaced those now, R3 and R45 are now in series with each other. So I now have a series right here. So what I could do is I could find the equivalent resistance of those two components, R45 and R3, and I could replace those with a single resistor, which I can call R345. And then if I picture R345 is the only thing now left in this branch. It is in parallel with R2. So what I could do is I could take this section here and I could say, all right, I can replace all of that with a single resistor, which I can call R2345 to simplify that down. And then what I have, it's kind of hard to see because it's layer on top of layer here, but if I go from the positive side of my power supply through R2345, I come back through R6, I now have a series circuit, and that would have an equivalent resistance REQ. So as I mentioned, we're going to start with these two 8 ohm resistors that are in parallel. So I'm going to try and find R45, which is their equivalent resistance. Now, because they're in parallel, I know that the reciprocals will add. So 1 over R45 has to equal 1 over R4 plus 1 over R5. So with that, this is one of those times where I will allow you to plug in numbers early rather than once at the very end of the problem, because the algebra on these gets insane. So what we're going to do is I'm going to say that 1 over R45 is equal to 1 over 8 ohms plus 1 over 8 ohms. So if I was to add those, 1 over R45 is going to be 2 over 8 ohms. And then if I take the reciprocal to actually find R45 is going to be 8 ohms over 2, which is just 4 ohms. And that's actually going to work out. If you have two components in parallel, if they're resistors in parallel, the equivalent resistance is always going to be half that of one of them, if they're identical. If they're not identical, it will always be less than any one individual resistor in that parallel circuit. It's kind of cool, because once again, you're providing an alternate path for the current to go through, which lowers the overall resistance in the parallel branch. So R45 is going to be 4 ohms. Now, the next part is we're completely ignoring these sections right here and pretend that they don't exist anymore. So all we have is in that branch now is R3 and R345, and those are in series with each other. So in series, R345 is just going to be R3 plus R45, because they're going to add. R3 is 6 ohms, R45 is 4 ohms, so those just add up to 10 ohms. So I can replace those two resistors with one resistor and call it R345, and that is going to equal 10 ohms. So I can pretend like that's not here anymore. So what I have now in that branch is just a single resistor, R345. That is now in parallel with resistor R2. So we're in parallel again. So you do 1 over my new equivalent resistance. I'm going to call this one R2345. Is going to be 1 over R2 plus 1 over R345. So we're going to have 1 over R2345 is going to equal 1 over 10 ohms plus 1 over 10 ohms. So 1 over R2345 is going to be 2 over 10 ohms. And now I can flip. Please, you cannot flip until you have a common denominator. So just recognize that. You can't just flip fractions willy-nilly. You have to get a single fraction with a common denominator before you do that. So R2345 is going to be 10 ohms over 2, which is just 5 ohms. And once again, R2345 is the result of a 10 ohm and a 10 ohm resistor in parallel, so my equivalent resistance should just be half of what any one individual one was. So now I'm going to pretend like neither of those branches are there. So this is gone and this is gone. And I'm replacing that with a single component, which I'm now calling R2345, which has a 5 ohm value. And then when I take a look I have this big loop right here, which is now all in series. So I can find the overall equivalent resistance is going to be R1 plus R2, 3, 4, 5 plus R6 all in series. R1 is 1 ohm, R2, 3, 4, 5 is 5 ohms, R6 is 3 ohms. So we get an equivalent resistance of 9 ohms. Now, I didn't ask for that in the problem, but I need to find that, because now that I know my equivalent resistance, I can find my current draw from the battery, which is going to be I0. And that current draw from the battery is going to be equal to my voltage of my power supply, which is E over Req. E is 9 volts, Req is 9 ohms, so I0 is 1 amp. So there is a 1 amp current being drawn from my power supply. So equivalent resistance and then Ohm's law to find the current from the power supply. So that was the first part. All right, so I've set some of the information that we have found aside. It kind of cleared up the screen a little bit, because our next part is to find the current in the 6 ohm resistor. So this is a little bit more of a puzzle. So this is where I have lots of different options. There's 2 different approaches that I can use. One, I can keep using what I know about series and parallel circuits and Ohm's law to kind of work my way down and find that current. I'd probably have to find a lot of other things along the way. The other thing I could do is start analyzing some of my loops and junctions, and I might have to use a combination of both. So when I get to this point, it's pretty straightforward to find equivalent resistance and then to find the current draw from the battery. But with all of these different branches going on, there are so many different ways and orders you can go about finding things. So the way my brain works may not be the same way your brain works, which may not be the same way the person on Khan Academy or YouTube or whatever thinks. So there are so many different ways to solve these problems. What's important, though, is that you are clear in your approach, which means don't do work in your head. Put your assumptions down on paper, trying to keep in mind, are you using a series rule, a parallel rule, are you using a junction, a loop? What are you doing? All of your assumptions do need to go down on paper. But the way it looks can be varied. You need to be able to pull yourself back and look at your work and make sure, can someone who is not inside my brain understand what I just did by just looking at my paper? And that's difficult. So keep that in mind. Your process has to be clear no matter what approach you use. So as I look at this problem, the one thing I know is when I start tracing currents, that anywhere that is attached to my power supply before a junction is going to have I0. So my current through resistor R1 is I0. My current through resistor R6 right here is I0. And we already found that. That's 1 amp. As soon as I0 reaches this junction, I now have a separate current, which I'm going to call I2, coming out of R2. There is going to be a current, I3, that then comes that way. So I have I0 coming into that junction and I2 and I3 coming out. So that's one thing I know. I also know that when I3 hits this junction, I'm going to have 2 different currents coming through here. I'm going to have what I'm going to call I4 and I5. And that those have to come back together, and my current here has to be I3 again, because I2 has to come into I3 and to create I0 again. Now, there's a couple of things that I know because I found some of my equivalent resistances. For example, I know that when I take a look here at that split, that this equivalent resistance here was R345, and it was 10 ohms. So what I can assume is that when I reach this junction right here, my current splits into I2 and I3, and the net result of this complicated bit right here has the same resistance as what's going on in the branch with just R2 in it. So what that tells me is it tells me that they actually have to have the exact same current. So therefore, I2 and I3 have to be identical, and they have to be half of I0. So the current through the 6 ohm resistor is what I'm looking for, which is I3. So I3 has to be half of 1 amp, so it's going to be 0.5 amps. So that's one way I could have gone about finding that value. What's another way? So let me pause here. What if I didn't notice that those two branches would have to have the current split equally? What else could I have done to solve this problem? Well, one thing I could have done is I could have chosen a loop. So I'm actually going to choose a loop this way. And I can choose that loop. The reason I want to choose that loop is that I know that all of those, that is actually a nice simple series. Well, it's not really a series loop, but it's a pretty simple loop. And if I was to write out that loop rule, I would have E minus I0R1 minus I2R2 minus I0R6 has to equal 0, because those are the components that I have to pass through in that loop. The reason I did this is because I know everything in that equation except for I2. So what this tells me is that I2R2 has to equal E, actually what is it at? Minus I0R1 minus I0R6. So that tells me that I2 is E minus I0R1 minus I0R6 all over R2. And if I plug in, E is 9 volts, I0 is 1 amp, R1 is 1 ohm, I0 is 1 amp, R6 is 3 ohms, all over R2, which is 10 ohms. So I get 9 volts minus 1 volt, because this right here is 1 volt, minus 3 volts. So that gives me 9 minus 4, which is 5. So that gives me 5 volts over 10 ohms, which is 0.5 amps. So using that loop, I found that I2 was equal to 0.5 amps. And then using this junction, I could say that I0 has to equal I2 plus I3. I lost a little 3 there. I2 plus I3. So that means I3 has to equal I0 minus I2. So I3 has to equal 1 amp minus 0.5 amps, which is 0.5 amps. Same answer, completely different method. So whatever you do, whatever method you do, notice that when I'm showing my work, you can see my thought process. You can see if I'm using Ohm's law, you can see if I'm using a junction rule, you can see if I'm assuming something, and why as you go through. The one thing you want to make sure is that your paper doesn't get super crowded. I'm really limited on space here. I try and give you space, but if you work on the left side of the paper and then the right side of the paper and the center of the paper, draw some arrows so I know what order you did things in. Or number the steps. Step number 1 was this. Step number 2 was this. Okay? Go through and kind of label things to help me out.